This is the third presentation in Unit 2. It's entitled Think Fast. And this is going to be an introduction into the vertical kinematics, things that move up and down, as well as our third major motion equation. So the learning goals. Students will be able to determine situations in which final velocity cannot be measured, determine the origin of the third motion equation, and determine an unknown in this particular equation. So here's what we already know. We know that acceleration is the rate of change in velocity. We know velocity is the rate of change in position. And we know that when something is dropped, that it initially has a velocity of 0 meters per second. Here's what we learned in the lab. That the relationship between time and distance when an object is dropped is no longer linear. So the difference between 1 second and 2 seconds is not just twice as much distance. That the greater the distance, the greater the time, and that some of you are not good at catching meter sticks. So that's what we learned in the Think Fast investigation. We also looked at this particular equation. It's a delta D is equal to VIT plus 1/2 AT squared. This is an equation that doesn't have final velocity in it. Our two previous equations both had final velocity in it. Here's where it comes from. It comes from the fact that we have our two motion equations that we're familiar with, and what we did is we actually took this equation and we rearranged it to solve for final velocity. Whenever we rearranged it to solve for final velocity, that's what we did here. We rearranged it to solve for final velocity. Once we had it equal to final velocity, I can take this term right here and substitute it in. When I do that and I simplify, this is the equation that I get. So this is called our accelerated motion equation. Once again, you have the same variables associated that we've had with the previous two. You have displacement, time, initial velocity, acceleration. Pay particular attention to the units because that's the easiest way to identify what value a number is. So if I say 100, is it 100 meters, 100 seconds, 100 meters per second? That last thing, the unit, allows you to identify what the variable is. So let's look at an example of this equation. It says determine the total displacement of a car that is initially traveling at 10 meters per second, but then accelerates for 2 meters per second for 5 seconds. So we're trying to figure out the total displacement of a car. Well, if we were to look at this, I'm looking for delta D, that's the displacement. I have the initial velocity is 10 meters per second. I have the acceleration is 2 meters per second squared. I have the time is 5 seconds. Using this information right here, I can go ahead and plug it into the equation. Delta D equals VIT plus 1/2 AT squared. When I do that, I can go ahead and solve. Delta D is equal to 10 times 5 plus 1/2 of 2 times 5 squared. Next, you would go ahead and put this into the calculator. You would say 10 times 5 is 50, plus 1/2 of 2 cancels out. 5 squared is 25. You would say that the total displacement of this particular car is 75 meters. Now, an interesting part is this would be if it didn't accelerate. This is the part in which you're dealing with the acceleration of this particular object. The next example, it says determine the initial velocity. Now, that's what we're trying to solve for, of a car that decelerates, okay, that's a key word, decelerates at 2 meters per second squared for 10 seconds when moving in the positive x direction of 500 meters. So with this information right here, what we're going to be able to do is we're going to be able to calculate the initial velocity. So we start off and we say initial velocity is what we're looking for. We would say the acceleration is actually a negative 2 meters per second squared. We would say that the time is 10 seconds and that the displacement is 500 meters. Now we can go ahead and solve in the equation delta D equals VIT plus 1/2 AT squared. In this case, we have the displacement is 500. We know that that equals to VI, and our T is 10, plus 1/2, and this time we have negative 2 times 10 squared. So let's go ahead and rearrange this a little bit. We're going to say 500 is equal to 10 VI. It's a little bit easier when you look at it in those terms. And now this 1/2 and this 2 are going to kind of cancel and just leave a minus sign. And then 10 squared is 100. So now we can rearrange. We can say that add 100 to both sides, and we get 600 is equal to 10 VI. Divide both sides by 10, and what we're left with is that 60 equals VI, or 60 meters per second, which is an incredibly fast speed for a car. In the next example, it says determine the acceleration of a missile that starts from rest and accelerates for 2 seconds over 84 meters. So if we look at it, we're trying to determine the acceleration. We know it starts from rest and accelerates for 2 seconds over 84 meters. So we know we're trying to solve for A. We know that we have the time is 2 seconds. Oh, we missed the initial velocity being 0. And we also know that the displacement is 84 meters. Using this information, we can plug it into the equation delta D equals VIT plus 1/2 AT squared. Or we can start to plug our numbers in. 84 equals 0 times T plus 1/2 of A T squared. Now, if you look, that's 2. 0 times anything, 2t, doesn't matter, is going to be 0. So this whole term is going to cancel out. So what I'm left with is 84 is equal to 1/2 of 2 squared. 2 squared is 4. So 4 divided by 2 is 2. You get 2a. Divide both sides by 2, and you get the acceleration is equal to 42 meters per second squared. S, meters per second squared. So far, all the situations we've covered have been horizontal ones. In other words, a car going down the street, a person walking, somebody running, something along those lines. They've been moving in the horizontal. But that's only part of what we're going to look at. The other half is the vertical situations. In other words, whenever you have an object that moves up and down. Now, you did look at some of this a little bit whenever you looked at a meter stick, and we said that when an object was dropped, that it initially has a velocity of 0, which makes complete and total sense, because if an object is dropped, just before it's dropped, it's not moving at all. We also know that the acceleration of these particular objects is negative 9.8 meters per second squared, or 9.8 meters per second squared down. Okay, this down is just indicating that it's negative. We always refer to up as being positive and down as being negative, just like we refer to right as positive and left as negative. That's kind of what we do in math class as well, so it should make sense. And we should know that our final velocity should be down. Whenever something's dropped, it's going to move down. It's not going to shoot up. We also know that when an object is thrown down, we know that its initial velocity is down. It's also going to be negative. We also know the final velocity is going to be down. And you should recognize that the final velocity of an object that's thrown down is going to be greater in terms of magnitude. It's going to have a higher speed than an object that is dropped. So the vertical information a lot of times is not explicitly stated. It's just an object is dropped and you're supposed to know. Another one of those things that you're supposed to know by being able to read the situation is at the highest point. Whenever an object reaches its highest point, the velocity at that highest point is 0. Now, whether that's the object's initial velocity because it's dropped, or whether it's fired up or thrown up in the air and reaching its highest point, regardless, the velocity is 0 at that highest point. The acceleration is always negative 9.8 meters per second squared. So now let's take this information that we've learned in the vertical and let's try and apply some of the previous information that we've learned using vertical problems. So the first one says determine the displacement of a ball 3 minutes after it was dropped. So we're looking for the displacement. Okay, so we're going to circle that. We have the time of 3 minutes. And a lot of people say that's only one thing, that's not enough, but that is not the case. So you have a time of 3 minutes, which you know 3 minutes isn't going to work. So we say 1 minute, 60 seconds, and I know that's 180 seconds. Next, you would say it's dropped, so the initial velocity is 0, and the acceleration is negative 9.8 meters per second squared. I'm trying to solve for the displacement. So the equation that I've had that related these variables together was delta D equals VIT plus 1/2 AT squared. Now in this case, The initial velocity is 0, so this entire term is going to cancel out. 0 times t, or 0 times 180, is still 0. Now plus 1 half negative 9.8 times 180 squared. Now the first thing that you should realize is that when you do this, you're going to get a negative number. So you multiply half, or 0.5, times 9.8, which is negative, times 180 squared. When you do that, you get a really large number of minus 158,760 meters. Now, some people have a hard time recognizing this negative symbol. Remember, the negative symbol just indicates the direction. It means that the ball fell 158,760 meters. Okay, so that makes sense when you drop a ball that it falls towards the ground. In the second example, it says determine the time a ball is in the air if dropped from a 10,000 meter tall mountain. So once again, we're trying to solve for time, and we have the displacement. Now when you do this, you once again have the initial velocity of 0 and the acceleration of negative 9.8 meters per second squared. The trick is in the displacement. The displacement is not 10,000 meters because when you drop a ball, the ball will not move 10,000 meters. Instead, it will move negative 10,000 meters because the ball will fall. Okay, if you put a positive there, you're indicating that the ball is going up, and it's not. So now you would, once again, we're trying to solve for time. You would use the equation delta D equals VIT plus 1 half AT squared. You would plug in, you would say delta D, which is negative 10,000, equals 0. That's going to cancel out that whole term, plus 1 half negative 9.8 T squared. Or negative 10,000 equals negative 4.9 T squared. You would divide both sides by negative 4.9. When you do that, 10,000 divided by 4.9 is going to cancel. Those negative signs cancel out. You get 2040 equals t squared. Okay, that's not the answer. You need to take the square root of both sides, and when you do that, you take the square root of 2040, you get 45.2 seconds equals time.